Okay, so I said this is the less simple stuff because it's thread synchronization and coordination, which in general are which are complicated. And you can talk about thread synchronization and coordination at multiple levels of abstraction. So I actually teach this stuff in our CS2 course, which is 401. And I'm pretty sure, and we'll test this out, that the students who took 401 from me have forgotten most of this. But the guys who did operating systems probably understand this a little bit deeper. And that's because the implementation was, the discussion was more implementation based. And that is how traditionally threads and thread synchronization have been taught. But since OS is not a required course, I wanted to teach threads in a required course. So what I will do right now is pretty much reproduce a discussion in the 401 class, okay? And we'll see how much 401 guys have retained. And it's a reflection of both you and me, okay, how much you retained. And for those of you who have not done 401 from me, maybe you'll learn something new, okay? And those of you who've never seen threads, hopefully you'll learn the most, okay? So it's, teaching threads using implementation focus, there's a well-defined way to do so, okay? Teaching it in CS2 is very unconventional. So I needed some philosophy, some principle to teach threads at that level, okay? Especially if I want to teach just not how to create threads, but also thread synchronization and coordination. And the theme I used was objects in motion, okay? And already we've seen this idea. When I introduced threads to you, and I wanted to explain to you what interleaving was and concurrency was, I took the analogy of a juggler juggling balls around, okay? So that was objects in motion, okay? And we can take other analogies too, like cars moving and a relay race and a shuttle moving. So we are going to talk about examples that are not OS specific, that are not distribution specific, but that are just objects in motion, okay? And that will provide us with analogies to understand threads, and also will give us good examples to understand threads, and more important, to visualize thread execution, okay? One way to visualize algorithms, if you haven't ever done this, and you probably haven't, you should Google for sorting out sorting, okay? It's a wonderful video produced at Toronto by a guy called Becker to show how sorting works visually, okay? And that particular sorting out sorting video came out when I was a student, so this is a pretty old video, okay? And it started a whole new direction in computer science called, where you were animating to teach, okay? And so the idea there was that you were teaching algorithm by animating them. So you just wrote an algorithm, and some external animation engine, and there's a lot of research that's gone on in creating these engines, took your algorithm and animated it, okay? So for instance, a guy called John Sopko, I'm saying John Sopko, and I'm totally blanking out here, but one of my friends at Georgia Tech, whose name I'm just forgetting, is like Sopko, created this animation engine that called Tango that would animate any algorithm. What we're going to do here is actually use animation. We're going to have animations in our code. So we are going to create animations, okay, to do the illustration. So other than having an external animator animating an algorithm, I will illustrate to you algorithms in which the animation is part of the goal, okay? And that will help us visualize the concurrency, okay? And what we're going to do is animate physical objects. Animate the motion of physical objects. And that makes sense if I'm teaching a course like 401, which is object-oriented, on object-oriented programming languages. That makes sense because object-oriented languages were initially created for simulations. The first object-oriented language was Simula 67, invented at Bell Labs. So it kind of makes sense to go and take examples involving simulations, okay? So that's giving you the broad theme that we're going to follow till I run out of time or run out of the deck. Okay. So we're going to take as an example movement of a shuttle. So this is the shuttle icon that I got by Googling and getting from Google Images. And the shuttle is at a certain position, okay, in the X and Y plane. And we're going to define an animate from origin method, which will go and make it come to 0, 0, and then make it come animate back to its original position. Okay, that's why animate from origin. And it's going to go first in the Y direction, up, and then it's going to go in the X direction till it reaches its final destination. Okay, it's a simple problem. And this is how we're going to implement it. So I said we are going to expose the implementation. We're not going to hide the implementation. Our algorithm has the implementation in it. And this is 401. I have to go and teach them modularity, which means separation of concerns. You keep functionality that is independent of other functionality in separate objects. Okay. So we're going to have a shuttle that moves. We're going to call that a plotted shuttle because it moves in a Cartesian plane with XY axis. We could put animation into it, but we can have shuttles that are not animated, and we can have multiple ways of animating the same shuttle. So we're going to put the animator in a separate object. Okay, we're going to call that shuttle animator, and that is the object on which we go and execute animate from origin. And the main class is also uncluttered. The main class can use many animators, so the main class is separate. Okay, so the main method we'll call animate from origin. Animate from origin will call set shuttle X and set shuttle Y repeatedly to animate the shuttle. Okay. And in a 401-like class, I need applications in which I can have multiple objects so that I can show the power of objects talking to each other. Okay. If all I have is one main class with a main method, I mean, you might as well be programming in C. Okay. So this is good that we have multiple objects. Okay. And how can we create concurrency here? Well, we can have multiple shuttles animating at the same time. Okay. So we have multiple shuttles animating independently. So we have multiple shuttle objects, multiple animator objects. Okay. And we'd like to go and animate them concurrently. So that means we should be using the runnable to go and executed by threads. So the run method will call animate, will go and reference the shuttle animator. And the runnables run methods are called by the start methods of thread object. Okay, we saw that. That's how threads are done. And the main thread will call the main method of the main class, which will create two threads, bind them to two different runnables, and then call the start method in both of them. Okay. And I'm saying animate shuttle here. I guess I should have said animate from shuttle from origin. I was just saving on the box size here, I guess. Okay. So that's our scenario. And based on what we have learned already, this should make sense given the problem we have. Okay. And let me just show you the concurrency right here. So we go and we have two shuttles now animating independently. So you literally see the two threads execute or interleave, either interleave or execute in parallel, because they reflect the movements, they control the movements of two different shuttles. Okay, so that's our thread creation description. Okay, so let's go and now. So we've done this. What I've shown in bold is that we've motivated and visualized concurrency abstractions of threads. So that brings us to the main topic of this slide deck, which is synchronization and thread coordination, and what we exactly mean. Okay. So synchronization. Let's talk about that first. That is relevant when there is some sharing among threads. Okay. And going back to the physical objects, if we assume that the two physical objects are cars, then sharing a road is like sharing a computer or sharing the same process. Okay, so two threads in the same process are like two cars on the same road. Okay. Now, we don't always need synchronization when we have two threads. Okay. So in the physical analogy, the cars can be in separate lanes, in which case it doesn't matter what the other car is doing. Or they can be in the same lane. Okay? And in the same lane, they have to synchronize with each other. Okay? You shouldn't be tailgating, and more important, you shouldn't be going in the opposite direction. Okay? So that is like accessing the same resource, two threads within the same process, accessing the same object or objects. Okay? You can have two threads that access independent objects, in which case we don't have any synchronization needs. Okay? But this sort of brings in synchronization. Okay? So synchronization has to do with sharing of objects and resources. So the two shuttles I just created did not need any synchronization. There were two shuttles that just went independently, and we didn't have to worry about the synchronization. Okay? So how do we make this a synchronization scenario? We can have two animators trying to control the same shuttle. Okay? And now things get interesting. Okay? So they both have animate from origin methods and or animate shuttle methods, and the question is, what can go wrong here? So actually, I'm sorry, in this case what we have is two threads accessing the same animator, and so not two animators, the same animator, but two threads executing it. Okay, so two threads saying animate shuttle independent. Okay. So in terms of visualization, what do you expect at this point? Basically, there'll be a tug of war, which will make the shuttle oscillate between two trajectories. Okay, and let's see if that really happens. Okay, so you literally see interference between the two threads. Okay, so you see here the reason why there was interference that you saw in the video. You have two threads here. They're both executing the same code, and in Eclipse you can see the thread stack of each thread one at a time. So right now I'm seeing seeing where the top thread is. Okay, and it's in the middle of this procedure, this loop that is setting the shuttle Y. Okay, according to the trajectory it has computed. And if I go and select the next thread, I see I'm in the same method, and this thread is also changing the Y of the shuttle according to its trajectory. So interference would be natural. Okay. So that brings us, for those of you who've done OS, so how do you, if you want to prevent that interference, we need something, and that something in the abstract is called a critical section. And critical section is a section, that piece of code that you just can't execute just because you want to. Okay, there has to be some condition met before you can execute it. Okay, and typically other threads should not be writing the data accessed by the critical section. Okay, so if no other thread is writing the data that you're accessing, you can execute. If somebody is, you should not. Okay, and so there's a lock associated with it. There's a guard. Okay, and just because you reach that critical section doesn't mean you can execute it. You have to pass the guard. Okay, and often code is called thread safe or synchronized if code has got critical sections in it. Okay, that means the conditions that are required to execute the code are actually honored, and we don't just are enforced. We don't just hope for the best or expect somehow the application to make sure that these conditions don't hold true. Okay. So a question is how to support critical sections, and those of you who've done OS have probably seen many mechanisms. So in Java we have what the solutions can be low level, they can be efficient or not efficient, and in Java it's a high level solution and it's efficient, and we connect this lock that I said critical section has to the data and methods that manipulate them. Okay? And as Andrew pointed out, we have the notion of a synchronized method to do so. We see here that animate from origin has been synchronized. So we put the synchronized keyword there to make sure that bad things, the interference doesn't occur. Okay. So this is, if you want to make some piece of code a critical section, if that piece of code is in a method, make that method synchronized. There's also a synchronized statement. You can take any block of code and put synchronized this or synchronize some object around that block of code, and you will make it synchronized. Okay. So let's just talk about synchronized methods. So we kind of intuitively understand what's going on here. So my next question to you is, what special processing occurs or happens on entry and exit of synchronized method? When an object is locked by a thread, other threads wait in a queue on entry. And when an object is unlocked on exit, the first waiting thread executes it. Okay? So the queue that these threads go into is called the entry queue. Okay? And that's how synchronized methods work. Okay? And all synchronized methods invoked on a particular object share a single entry queue. Okay. Here's a graphic to illustrate what happens with synchronized methods, how the blocking takes place. So when a thread goes and executes this method, it's synchronized, but the object is not locked. So it puts a lock on the object saying nobody else should enter this object while I'm executing synchronized method. And if another thread now tries to go and execute this method, it is put in a wait state. It goes into a queue. Okay, it doesn't get to execute the method. So when you have synchronized methods in a class, that class is called a monitor, and the synchronized methods traditionally have been called entry procedures or entry methods. Okay. So we can do the same problem we did earlier, but now we're synchronized. So again, there are two threads trying to change the same shuttle, and you see now one thread finishes its task, and then the second thread goes and finishes because we synchronized that method. And I'm going to delay questions till there's a point. So we've seen synchronization, and let's look at thread coordination. Okay. And there are these related terms: coordination, synchronization, mutual exclusion, and there are different interpretations of this. So I'm just going to give you one set of interpretations, and hopefully I'll be consistent. Okay. So we'll say threads are synchronized in general if a thread waiting for another thread, if the thread waits for another thread to do something. Okay? And you can wait for another thread because you want mutual exclusion. That thread has got something that you want. You don't even care what the other thread is doing. Okay? It's just that that thread is stopped at this stop sign, so you can't proceed till that thread goes away, and then you can go further. So this is sort of a situation where threads are competing for something, and you're just being nice and putting yourself in a queue so that that thread can be serviced, and then you can be serviced later. Okay. Another situation is that the two threads are related to each other. One thread depends on another thread for its task. This is the coupled situation. Okay, and we're going to call synchronization that does not involve mutual exclusion as thread coordination. Okay. And here the threads are cooperating rather than computing, explicitly waiting for actions of others depending on these actions to be finished. Okay. So these are the two situations. And we've looked at mutual exclusion very quickly. Those of you who've done operating systems have seen spinning and semaphores and other mechanisms and seen the trade-off among them. We are focusing on Java, so I'm going to just focus on how Java does things. Okay. So let's look at an example involving our shuttles. So now we have two animations, and we also have a third thread that decides when these animations proceed. Okay, so what will happen is that we will go and call animate from origin on both of these shuttles with two different animators. But these these animators are going to wait for a signal from the third thread before they proceed. Okay, and that signal is given by the user. So the third thread is managing user interaction, and when the user goes and says proceed, then the first waiting shuttle will animate, and when the user says proceed again, the second shuttle the second shuttle will go. Okay, so let's see whether that really happens or not. Okay, so we are animating shuttle, they're both waiting. I said proceed, and this shuttle starts moving. And I say proceed again, and the next shuttle starts moving. Okay, so this is not pure mutual exclusion. These threads were waiting for me, a cue from me. So the human and the animation are cooperating with each other, and the human is represented by a thread. Okay, so the question is, how does a thread wait for an event? Okay, we need as implementers to know how this was really programmed. And in Java, there is something called wait, and there's something called notify. And wait is what makes a thread block, and notify is what makes a waiting thread unblock. Okay, so this we have wait and notify. As it turns out, if you notice that I'm using both mutual exclusion and coordination here, the wait and notify are executed in synchronized methods. Okay, and if you don't do that, if you don't execute them in synchronized methods, Java will let you write the code, but at runtime it will give you an illegal monitor state exception. Okay, so the question is, why should wait and notify be implemented, which are implemented by object, by the way? Okay, so wait and notify can be executed on any object. Why must they be executed in synchronized methods? Surely, we are talking thread coordination, not mutual exclusion. So why do we have to do mutual exclusion to do thread coordination? Okay, and by the way, proceed is invoked by the AWT UI thread, and wait for proceed is called by the waiting shuttle animator thread. Okay, so the reason why we need mutual exclusion to implement coordination is that coordination involves a shared data structure, which is the wait queue or the condition queue. So we need atomic access to the queue itself to do process coordination. Okay, otherwise the queue can be left in an illegal state and can be left in the middle. So that is why they have to be they have to be synchronized. Okay. So wait and notify implemented by object must be executed in synchronized methods as they access a shared wait queue. Okay. So we see what happens here now. The a waiting thread executes a synchronized method. A thread that may wait executes a synchronized method in which a wait call occurs. Right? That's a situation that you want to wait, but the wait must occur in a synchronized method. That means before the wait, the thread that executes the thread that's about to execute the wait has got the object lock. Okay, so should it release the lock before waiting, or should it keep the lock? So wait releases synchronized lock on object, and as was said, that we want to go and release the lock so that a notifying object can execute a synchronized method that goes and unblocks it later. Okay, so if you don't release the lock, then you'll never be woken up, and you'll just keep the lock forever. Okay. What about notify? When you execute notify, do you release, again you're in a synchronized method, and after notify, do you continue executing, or do you release the lock? Okay, that's my next question for you. So the answer, I think, based on all the answers we got, is no. It could, as was mentioned, there are multiple approaches. It could release the lock, or it may not. And as Andrew pointed out, the notifier can just continue doing and at some point later release the lock. And at that point, the waiter can enter potentially. Okay, and that's what happens in Java. Okay, and it's called the hint approach. And a little later, we'll go and see why it's called the hint approach. But the reason for the hint was pretty much given in the answer to the previous. So what's your name? Okay, again, I asked you the second time I'm asking you. Okay. But the analogy is that one thread is enabling another thread to go. So again, taking our objects in motion analogy, it's not that two cars are trying to go and compete with each other for the same spot. It's as if that one car is waiting for another car, or one runner is waiting for another runner to complete, and then the runner can proceed later. Okay. So this is our wait for proceed, and this is our proceed. And wait for proceed, as we know, call made the wait call, and proceed made the notify call. Here's a graphic to show you how wait and notify work and what the blocking semantics are. So in the example we saw, we had an object called a clearance manager with methods proceed and wait for proceed. These are not standard methods. These are methods that object defined. They are synchronized because we require wait and notify to be in synchronized methods. Wait and notify themselves to be called in synchronized methods. Wait and notify themselves are not synchronized. They're defined by the class object. They're final methods. You can't override them. And let's see how the interaction we saw in the graphics takes place here. Okay. So a shuttle animation thread calls wait for proceed before it really starts animating. And that method in turn, so because it's a synchronized method, it gets the object lock, enters the method. The method in turn calls wait. Okay. So it's put in the wait state. Okay. And it releases a lock. So that somebody else can enter the monitor and notify it and release it. Okay. And so when wait releases synchronized lock on object and makes the calling thread wait in a queue, and that queue we'll call a condition queue. And it lets some other thread get the synchronized lock so that the thread can do its task, and more importantly, the thread can wake it up. So when the user presses proceed, this is processed by the AWD thread, which goes and calls proceed. It needs a lock. Fortunately, the lock has been released. So it gets a lock, calls notify, and that goes and takes the animation thread away from the condition queue. Now, where it goes next is, there are multiple choices we saw last time. And there's the hint and absolute approach. And the AW thread then returns from proceed and releases a lock. Okay. And now the shuttle animation thread can enter this procedure. Okay. Resume execution of its procedure. So it gets the lock. Okay. The lock has been released by the notifying thread, and it can then finish its wait and return. Okay, so that's what's happening with wait and notify. And when it returns, of course, it releases a lock again. So there's a shared queue, and it is in that shared queue that the waiter gets put. It's that shared queue from the shared queue that the waiter is released during execution of the proceed but method, and that is why So that's what happens during the execution of the notify method, and that's why wait and notify must be executed in synchronized methods. Okay, let's continue with this. We now have another button called proceed all. Okay, and so again, the two shuttles, when we go and try to animate them, they will wait for a signal, and when we do proceed all, both shuttles will go and start racing with each other. Okay, so let's go and do the animation here. Animate one, animate the other, and then proceed all, and both of them get unblocked. Okay, so this is a situation where more than one thread is unblocked by one action. Okay, and the analogy here is a policeman saying, "Okay, everybody now in this direction can start moving," or in a relay race, a person saying, "Okay, here's a signal for all of you to start running." Okay, so we see this happen in real life, and pretty much that is what was happening in our simulation also. Okay. So this is proceed all, and the example of a baton being exchanged between two runners is an example of just proceed or notify. Okay, so everyone waiting proceeds, and one person proceeds. And so proceed all is just calling the Java notify all in a synchronized method. That's the only difference. Okay, so notify all by itself is not a synchronized method. So we go and put it in a proceed all method that is synchronized. Okay, and here's the wait queue visualization. So when the two threads, when the two shuttles or two threads were waiting, they were both put in this queue. Okay, and when proceed, so this when we were doing just a single proceed, then one thread is released and the other thread stays in the queue. When I do another proceed, both of them get removed from the queue. And with proceed all, very similar situation, except that when you do a proceed all, both threads get unblocked from the queue. Okay, so I actually visualized the queue in this animation here. Okay, so we've seen three new methods. These methods are provided with a class object. Class object, as you know, defines a lot of methods like toString, equals. You might or might not have used clone. But if you ever use Eclipse, it also gives you the alternative to calling wait, notify, notify all. And when you execute wait on an object, it makes the calling thread block in a wait or condition queue. It's called a wait queue or a condition queue. We'll see why it's called condition soon. Notifies is if some threads are waiting as a result of o.wait, then it unblocks the very first one waiting, and notify all unblocks all of them. Okay. So when you make a wait, notify, or notify all call, there's always a target object. Okay, and that target object we'll call the synchronization or coordinating object, or the monitor of these calls. Okay, so each wait, notify, and notify all is associated with a certain object, which is the monitor or synchronizing object or coordinating object. Okay. So we see the analogies here: proceed versus proceed all, and there's also two kinds of coordination going on here. In the proceed all cases, there's an external agent that is coordinating the threads. Okay, so there are the runners that are actually going and executing, and there's another one whose job is to coordinate. Okay, in the case of the proceed calls, the two threads are themselves coordinating. I'll call that internal coordination, and I'll call the left one external coordination. And all the visualizations I've shown you right now were examples of external coordination. Here was a user who was not actually doing the actions that are being coordinated, who was just signaling the actual actors. Okay, so that was external coordination, and I want to give you an example of internal coordination to bring in more concepts. Okay, so special coordination object, which is the clearance manager in our example, or the policeman, And here there's internal coordination, where there's no special coordination object, where the objects that are doing the actions are themselves coordinating. Okay. So here's an example now, the same shuttle example now with internal coordination. Okay. Now what's going to happen is that the threads, I have decided that going at making the shuttle move in the y direction at the same time is a bad idea. Okay, so each thread will wait for a previous thread to leave the y-axis, and when it has started moving in the x direction, it's only in that case will the thread animate. Okay, and these are three different y-axes actually. Okay, because each of them is a separate object, but they all know that there is a thread is moving in its y-axis. They somehow know that, and they make sure that when a thread is moving in its y-axis, they themselves wait. Okay, so this is what you'll see here. So I animate shuttle, it starts moving in its y direction, and the other two threads are waiting. It starts moving in its x direction, and one thread starts, the other thread, next thread starts executing, and so forth. Okay. So now these are three different objects, three different animators, three different shuttles. All of them are different objects, yet they are somehow coordinated, and they themselves do the coordination. They don't go and depend on another thread to go and do the coordination. But since they're all accessing different objects, we can't rely on one object to synchronize them. So we have separate y-axis, cannot synchronize on it. And even if axes were shared, we cannot really invoke any methods on the y-axis. So we need to build our own external object, not new thread, external thread. We'll build our own external object, which we'll call a lock object. And all of these threads will go and communicate through this lock object. Okay? And it's like reserving a bunch of rooms for a conference. So here's a lock, okay, separate object. It's got a get lock and a release lock. Okay. Chris mentioned that a notify can occur before the corresponding wait may occur. So what we do is we keep the state of the notification in this. So we have a Boolean that says whether this monitor is or this object is locked or not. If the notify comes first, it'll go and set the Boolean to false, saying it is not locked. So the waiter then comes later, it'll go and say, is it locked? If it's locked, I'll wait, otherwise I won't wait. If the waiter comes first, it finds it locked, it'll wait, and then when the release lock occurs, it'll set the lock to false and notify, and the waiter will find that the lock is false, so it'll proceed. Okay, so we have gone and overcome the timing issue that Chris mentioned earlier. Okay, and there's this one object that all shuttles keep track of. So now what happens is that all animators are passed this lock when they're created, and then internally, as soon as before making their movement along the y-axis, they try to get the lock, and after finishing movement along the y-axis, they release the lock. Okay. So animate y from origin goes and gets a lock before it's executed, and so I've defined a class that overrides the previous class. So the previous class had an animate y from origin that did not check for locks. I've got a new animator that gets a lock, calls the super method, lets it do the job, and then release the lock. Okay, and that lock is passed as an argument to the constructor. Okay, and let's go and now look at the lock, and like I said, and try to analyze this. And those of you who have not done OS probably find nothing wrong with this code, but those of you who've done OS, Please tell me what is wrong with this code. And I kind of know what you will say. So let me go and give you your answer. This should not have been an if, this should have been a while. Okay? And those of you who've not done OS are probably puzzled. So my question is, why is while safer than if? So this has to do with the fact that notify, my slides are a little off here, notify, let me go and see what I've got here. Yeah. So the fact that notify did not release the monitor lock, the object lock, it has to do with that fact. Okay. So when somebody doesn't notify, they are saying that some condition is that some blocking condition has become false now. At that point, not later point. At that point, the condition is the blocking condition has gone away. If it continues to execute, it may execute code itself that makes that condition invalid. Okay, and so if the notified thread does not get to execute immediately, then it's not guaranteed that the condition that it was waiting for is invalid, or is true now. That okay. So notify does not cause unblocked thread to immediately execute. Conditional unblocking true right after notify. So the notified thread, the unblocked thread, when it later executes, has to go and check the condition again to make sure that it is still true. Okay, the condition of unblocking has become false, and the condition of proceeding has become true. Okay, so that has to do with this. That has to do with this hinge semantics, and okay, and here's the hinge semantics again. So we said that must notify in a synchronized method release object lock to allow other threads to proceed. We said not really, and in Java it was not, and so that's why the hinge semantics. We go back here. Here's okay. So if we go back here now, things are a little confusing. Okay, and I've got 4 minutes to try to resolve the confusion, and I'm keeping track of the time. What exactly happens in notify if the waiting thread is not immediately executing? Remember, the waiting thread is waiting in a wait or condition queue, right? If when you do a notify, that thread starts executing, is unblocked and starts executing, then we know what that means. That's the absolute semantics. But now we are saying the notifying thread continues to execute. The unblocked thread does not execute the monitor. So where is the unblocked thread? What happens to the unblocked thread? Where does an unblocked thread go if it's not immediately executed? We haven't quite answered that explicitly. These guys who've been answering the questions have kind of assumed something. So let's go ahead and make that explicit. Yeah. If it is in the ready state, where is it? Which queue? I mean, if it is in the ready state, yeah. Okay, so you're saying it goes in a special queue called the urgent queue, which is a queue consisting of? Okay, good. And really there are two questions. There are two choices. One is that the unblocked thread indeed does not immediately resume execution. So the question is, where does it go? And the other question is, what if it does resume execution? We said that things can go either way. So if it immediately resumes execution, where does it go? Where does the notifying thread go in that case? Because the waiting thread has immediately started executing, the notifying thread hasn't finished executing the entry procedure, the synchronized method. So where does that go if the notifying thread is the one that's going to execute? Because both threads cannot execute their synchronized methods at the same time. Okay. So there are two approaches, hint and absolute. And in the hint approach, we need a while loop. We need the wait to be in a while loop. And in the absolute approach, we need the wait to be in an if. Okay. So let's come to the hint approach. So we know that the notified thread, the waiting thread, unblocked thread, cannot immediately start executing. Okay? But we must record the fact that it is no longer waiting. So it gets removed from the condition queue, and it has to be put in some queue. It needs to go and enter the monitor again. Okay? And normally the queue to enter the monitor is an entry queue. So it could just go and be put in the back of the entry queue. That means behind other threads that have come, that have executed since, that have come to the monitor since it entered the monitor. Okay? So that's not a very nice situation, because those threads in front can then go and enter the monitor, the frontmost thread enter the monitor, find the condition for execution true, and do its task before the older thread. And if enough new threads come in, the older thread may never execute. And when this occurs, we call it starvation. Okay? And that's why people tend to use queues rather than some other data structure, because queues normally reduce starvation problem. Okay? So the alternative to this is to put it in some front section of the queue, or in other words, to put it in a separate queue. We'll call that the urgent queue. And whenever the lock is released of the monitor, the urgent queue is serviced first, and then the older entry queue threads are serviced. Okay, so this way there's no starvation. What happens in the absolute approach? Now the unblocked thread immediately starts executing. So the notified thread is put in a queue. It has to re-enter the monitor to finish executing a synchronized method. Again, we don't want it to be starved. Here it is being nice. It's trying to unblock somebody, and it may never ever get to execute its method again, because there will be enough new threads coming in. Okay, so again we have an urgent queue, but in this urgent queue, it's a notifying thread rather than the notified thread that actually gets put. Okay, and so that urgent queue is serviced before the entry queue, and things proceed. And why do we say hint versus absolute? If the unblocked thread is not immediately executed, the condition for which it was waiting may no longer be true when it next enters the monitor. Okay? The only guarantee we have is that when notify is called, at that point the condition to proceed is true. One statement later, it may not be. Okay, the same method that went and notified may go and change that condition later. Okay, so unless that thread executes immediately, it's not guaranteed that its condition is true to proceed. Okay, so it must, when it resumes execution, it must check again whether the condition is true. Most probably, it will be true to proceed. But if it's not, just in case it's not, it has to go and re-wait. Okay, so that means when it's unblocked, unblocking it is a hint that the condition it's waiting for to proceed is true. It's not a guarantee that the condition to proceed is true. It must recheck it. In the absolute approach, unblocking it is an absolute guarantee that the condition to proceed is true, and it need not check the condition again. Okay? And that's why it's if versus while. And this is pretty advanced discussion, and typically this is done in operating systems. But if you're going to use Java and use Java's hint semantics, you need to know how to code. You need to know why you should put a while and not an if. Okay? And I don't want to just tell you put a while. I should explain to you why you should put a while. Okay? So that's the explanation. To summarize, we've done mutual exclusion and seen the associated concepts of critical section and synchronized methods in Java. We've seen process coordination and wait, notify, and notify all to implement that. We've seen the hint versus absolute semantics. And we've seen that each object has an entry queue and an urgent queue. Okay, for mutual so it has an entry queue for mutual exclusion and a single wait queue for process coordination, just one queue, and this wait queue is associated with an urgent queue also, okay, which can be thought of as the front of the entry queue. Okay, because you don't put things in the front of a queue, that's not a queue any longer. So think of that conceptually as an urgent queue.